Hi students, welcome to the first lecture in permutations and combinations. In this lecture we are going to cover these two topics: fundamental principle of counting and number of permutations of n distinct objects taken R at a time. We are going to derive the second one using the first one. Anyway, we'll look into these two in detail in this lecture itself. Permutations and combinations is a basis for probability and random variables. So if you miss permutations and combinations, you are going to miss probability and random variables. So you have to be a little bit careful with permutations and combinations, else you will be missing these three chapters. And coming to probability, you will have an entire course on probability in engineering first year or second year, whichever stream you take. So you cannot escape from probability, and thus you cannot escape from permutations and combinations. And this tells you how serious you have to be with permutations and combinations. And moreover, if you cannot understand permutations and combinations, it's going to be a nightmare for you. If you can understand permutations and combinations, you can really enjoy this chapter. So before understanding permutations and combinations, we have to understand the basic difference between ordinary brackets and braces. So you may have noticed that A comma B is different from B comma A. Because here the first element is A in LHS and the first element in RHS is B. And here the order of the elements matters. We can understand this using complex numbers also. You may have noticed that A comma B represents the complex number A plus IB, whereas B comma A represents the complex number B plus IA. And these two complex numbers are different because the real parts and imaginary parts here are different. Therefore, A comma B is different from B comma A. Whereas the set containing A comma B is same as the set containing B comma A. Because here there is no question of first element and second element. Whereas A comma B is different from B comma A. The set containing A comma B is same as the set containing B comma A. So similarly, the set containing X comma Y comma Z is same as the set containing Z comma Y comma X. These two are one and the same. Whereas the ordered pair X comma Y comma Z is not the same as Z comma Y comma X. X comma Y comma Z is not the same as Z comma Y comma X, because here the first element is X and here the first element is Z. So whenever order matters, we are going to use these brackets, and whenever order does not matter, we are going to use these braces. So likewise, whenever order matters, it is going to be a problem in permutation. Whenever order does not matter, it is going to be a problem in combination. So if you understand the difference between ordinary brackets and braces, you can understand the difference between permutations and combinations. Anyway, we haven't defined what is a permutation and what is a combination. So for the first few lectures, we are going to deal only with permutations. Before going into the definitions of permutations and combinations, let us look into one problem each for permutation and combination. So look at this problem. There are 4 different people or 4 children: Abhi, Bobby, Chanti and Dhruv. These 4 are labeled as A, B, C and D. And now these 4 wants to play gully cricket. And the question here is, they want to choose the batting order. There are 4 different batting orders, namely 1, 2, 3 and 4. 1 stands for first batting order, 2 stands for second batting order and 4 stands for fourth batting order. You may have come across this problem in your childhood, But what you haven't noticed is there are 24 different options. And I have listed all these 24 different options for you. By ABCD, what we mean is A, that is Abhi is going to bat first, B, that is Bobby is going to bat second, C, that is Santi is going to bat third, and D, Dhruv is going to bat fourth. And by DABC, what we mean is Dhruv is going to bat first, A, that is Abhi is going to bat second, Bobby is going to bat third, and C, Chanti is going to bat fourth. So there are 24 different batting options. So what happens if we keep on increasing the number of people? So those who are interested, they can look into this problem. A cricket team contains 11 people. So in how many ways these 11 people can go for batting? Anyway, we can answer this question in this lecture itself. Those who are interested, they can give a try now. Now consider this problem. There are 7 different people and there is one car which contains 4 seats. Now the question here is, we have to select 4 people from 7. So there are 7 people and we have to select 4 people. So in how many ways we can select 4 from 7? That is the question. And the answer is going to be 35. I cannot list down all the 35 options here. So you have to believe with me for this answer. So in the previous problem, the order matters. So this problem is a problem in permutations. In this problem, the order does not matter. All that it matters is whether a particular person is there in the car or not. So this problem is a problem in combinations. Anyway, in this chapter we are going to count how many permutations and how many combinations are there. So basically the motto of this chapter is to count the number of permutations and the number of combinations. So for this we have to develop some counting techniques. Already we are familiar with some few counting techniques, but these counting techniques are not sufficient. Anyway, we will look into these things. So here you have a chessboard. So the question is, how many unit squares are there in this chessboard? So without counting, you can answer that it contains 64. So it's a general knowledge question. Here there is no need of counting all the unit squares. And now look at this problem. How many unit squares are there in this grid? And so I cannot count the unit squares like this 1, 2, 3, 4, 5, 6, 7, 8, and then I cannot write 9, 10 and so on. What we do here is, there are 8 unit squares in this row and there are 4 such rows. Therefore the total number of unit squares is 8 times 4, which is going to be 32. So similarly in the above problem also there are 8 unit squares in each row and there are 8 such rows. Therefore the total number of unit squares is going to be 8 times 8, which is going to be 64. So if you know times tables, then you can count the number of unit squares here and the number of unit squares in this grid. Now look at this problem. So here the question is, how many balls are there here? The first row contains 1 ball, the second row contains 2 balls, third row 3 balls, fourth row 4 balls and fifth row 5 balls. So the total number of balls is going to be 1 plus 2 plus 3 plus 4 plus 5. So if you want to count, 1 plus 2 is 3, 3 plus 3 plus 4 plus 5, which is 6 plus 4 plus 5, which is 10 plus 5, which is 15. Anyway, we will not count in this way. We have come across this formula in your first year, that is summation I is equal to 1 to n I, which is equal to n times n plus 1 upon 2. So here instead of n we have 5. So the answer is going to be 5 times 5 plus 1 upon 2, which is equal to 5 times 6 upon 2, which is equal to 15. So instead of doing this labor work, we can use this formula to count the number of poles. If there are 10 such rows, then what happens? The answer is going to be 10 times 10 plus 1 upon 2, which is equal to 5 times 11, which is equal to 55. So with the help of this formula, we can reduce our efforts. So similarly, in order to count the number of permutations and number of combinations, we have to develop some counting techniques. And the special counting technique that we are going to develop in this chapter is the fundamental principle of counting. And before going into fundamental principle of counting, we will see what fundamental principle of counting is going to tell us. Now look at this problem. So you have 4 different colored trousers and 3 different colored shirts. And here the question is, you have to select a pair. By a pair, what we mean is, we have to select a trouser. We have to select a trouser and we have to select a shirt. So I repeat, by a pair we mean we have to select a trouser and we have to select a shirt. So in how many ways we can select a pair? That is the question. So here I have listed down all the different options that we have, and the answer is going to be 12. So we will see what are the 12 different options we have. By T1 S1 I mean we are selecting the first trouser and we are selecting the first shirt. And the next one, by T1 S2. By T1 S2 what we mean is we are selecting the first trouser and second shirt. Similarly T1 S3, T1 S4, and similarly T2 S1 and so on. So on the whole we have 12 different options. So the important word that you have to remember here is n. So whenever n comes, it's going to be a problem in multiplication. We will see those things. Okay. Now consider this problem. So you have 4 different trousers and 3 different colored shirts. Now in the previous problem we have to select a pair, but here in this problem you have to select one item. In how many ways you can select one item? That is, I can select one trouser or one shirt. So how many trousers we have? On the whole we have 4 trousers. And how many shirts we have? 3. So on the whole I have 4 different options plus 3 different options. So the total is going to be 7. So in 7 ways I can select one item from these 2. So I have to select one item. That means I have to select an item. I have to select a trouser or a shirt. The important word that you have to remember in this problem is R. And the important word that you have to remember here is AND. So whenever AND comes, we have to multiply. And whenever R comes, we have to add. If you understand these things, you can solve many problems in this chapter. Whenever AND comes, it's going to be multiplication. Whenever R comes, it's going to be addition. Now, let us look into the definition of fundamental principle of counting. If a work W1 can be performed in m different ways and another work W2 which is performed after W1 is being performed in n different ways, then the number of ways of completing W1 and W2 one after the other is going to be m times n. That is number of ways of doing W1 times number of ways of doing W2, which is going to be m times n. So here there are two works, W1 and W2. What we are doing is we are performing both the tasks one after the other. W1 and then we are going to perform W2. Therefore, the total number of ways of completing the work is m times n. Number of ways of completing W1 times number of ways of completing W2. We can understand this problem using this example. Suppose there are 4 different ways to go from A to B, and there are 3 different ways to go from B to C. Now the task is to go from A to C via B. So I repeat, the task is to go from A to C via B. So this task can be decomposed into 2 works, that is W1 and W2. So W1 is to go from A to B, W2 is to go from B to C. So in order to complete the task, what we have to do? We have to perform W1 and W2. We have to perform W1 and W2. Now, the number of ways of going from A to C is going to be number of ways of going from A to B times number of ways of going from B to C, which is going to be 4 times 3. So if you want to understand the principle, we can go back to the previous problem. Okay. So here the task is to select a pair. Our task is to select a pair. Select a pair means I have to select a trouser, which is W1, and I have to select a shirt, which is W2. And number of ways of completing the task is equal to number of ways of completing W1 into number of ways of completing W2. So which is 4 times 3, because we have 4 different trousers and 3 different shirts. So we can extend this fundamental principle of counting to a finite number of things. That is, if W1 can be performed in N1 ways, W2 can be performed in N2 ways, and Wk can be performed in Nk ways. Then the number of ways of completing all the works one after the other is going to be N1 times, N2 times, and so on up to Nk times. So here we are going to perform all the works. We are going to perform all the works one after the other. And the number of ways of completing the task is number of ways of completing W1, number of ways of completing W1 into number of ways of completing W2 into so on up to number of ways of completing Wk, which is going to be N1 times, N2 times, and so on up to Nk. So this is an extension for fundamental principle of counting. In the definition, we have seen only for 2 works, but we can extend it to finite number of things. If you extend it to finite number of things, this is the formula. Now, again we have fundamental principle of counting for addition. In the previous one, that is fundamental principle of counting multiplication, and this is for addition. Okay. So the definition is like this. Suppose a task can be performed in two different modes, W1 and W2. And W1 can be performed in m different ways, and W2 can be performed in n different ways. And the number of ways of completing the task is number of ways of completing W1 plus number of ways of completing W2. We can understand this definition using this example. And the example is like this. Suppose there are 3 different buses to go from Hyderabad to Bangalore. 3 different buses and 2 different trains to go from Hyderabad to Bangalore. Then the number of ways of going from Hyderabad to Bangalore, that is the question. I repeat, the question is how many number of ways are there to go from Hyderabad to Bangalore. So here you can select either a bus or a train to go from Hyderabad to Bangalore. If you select a bus, then the number of options that you have is 3. If you select a train, the number of options that you have is 2. So on the whole, the number of options that you have is 3 plus 2, which is going to be 5. So here this task contains 2 different modes, W1 and W2. W1 is choosing a bus. W2 is choosing a train. You can choose either W1 or you can choose W2. So the important thing that you have to notice here is we are not going to perform W1 and W2. We are going to perform only one of these two, either W1 or W2. In fundamental principle of counting, we are going to complete all the tasks. But here, the fundamental principle of counting in addition, we are going to complete only one task, only one work. So here we will have addition. So the important thing that you have to notice in this chapter is whenever end comes, we have to perform multiplication. Whenever R comes, we have to perform addition. So this is the basic thing that you should not forget in the entire chapter. So if you get messed with these things, then you cannot arrive at the correct answer. Okay, so there are a few notations. I think you are familiar with this factorial notation. If you are not familiar with the factorial notation, and it goes like this. We define 1 factorial as 1, and n factorial is defined as n times n minus 1 factorial. So you have to understand these two. 1 factorial is equal to 1, 1 factorial is equal to 1, and n factorial is equal to n times n minus 1 factorial. If you understand these two, we can define 2 factorial, 3 factorial, 4 factorial, and so on. So using these two, we can define 2 factorial. How we can define 2 factorial? 2 factorial is equal to 2 times 1 factorial, which is equal to 2 times 1. And how we define 3 factorial? 3 factorial is equal to 3 times 2 factorial, which is equal to 3 times 2 factorial is going to be 2 times 1, which is equal to 3 into 2 into 1. And 4 factorial is equal to 4 times 3 factorial, which is equal to 4 times 3 into 2 into 1. And similarly 5 factorial is equal to 5 into 4 into 3 into 2 into 1. We have to stop at 1. If you continue after 1, the result is going to be 0. So this factorial is defined in this way. Anyway, for the sake of convenience, we define 0 factorial is equal to 1. There is no special reason. 0 factorial is defined as 1 for the sake of convenience, so that we can use all these notations in the formulas without any exceptions. So you have to be a little bit familiar with factorial. We are going to use these factorials in this chapter. Anyway, there is no need to remember the values. 2 factorial is 2 into 1, 3 factorial is 3 into 2 into 1. There is no need to remember it as 6, and 4 factorial is going to be 4 into 3 into 2 into 1. No need to remember it as 24. All that you have to remember is this 4 factorial stands for this number 4 times 3 times 2 times 1. And 5 factorial stands for this number 5 times 4 times 3 times 2 times 1. So we have to keep on decreasing until 1, until we reach 1. So how do we define 10 factorial? 10 factorial is defined as 10 into 9 into 8 into 7 so on up to 2 into 1. So this is how we define factorial. So the next topic is to define permutations. So permutations are basically divided into 2 types or 2 groups. The first one is linear permutation and the second one is circular permutation. Anyway, there are some exceptions in circular permutations and linear permutations. We'll look into those things, but the basic picture is permutations are basically divided into 2 groups. The first group is linear permutations and the second group is circular permutations. We will deal with these circular permutations after this exercise, but first we will learn what do you mean by linear permutations. And the definition of linear permutation is like this. Definition: from a finite set of things. Those things can be similar or dissimilar. Selecting a few or all of them and arranging them in a row or in a line is called as a linear permutation. Instead of saying linear permutation, we just say it as permutation. But circular permutations are called as circular permutations, whereas linear permutations are called as permutations. So this is the definition we have. So this is the definition that they have given in the textbook. You can understand this definition in your own words. So if you want to understand the definition in your own words, the definition is like this. Permutation, you can define it as permutation is an ordered arrangement. Ordered arrangement means order is going to be matter here. An ordered arrangement is defined as a permutation. So instead of this boring definition, we can just remember this one. A permutation is an ordered arrangement. So look at the definition carefully. So we have from a finite set of things. Those things can be similar or distinct. Those things can be similar or distinct. And we can select all the things or a few. After selecting, we have to arrange them in a row. If you arrange them in a row, it's going to be a linear permutation. If you arrange them in a circle, it's going to be a circular permutation. Anyway, we'll look into circular permutations later. But first you have to understand the definition of linear permutation. Instead of calling it as a linear permutation, we will call it as just a permutation. So whenever you see the word permutation, you have to understand it as a linear permutation. Okay, so we can look into a few examples. And the first example is from the letters of the word mint. 2-letter permutations are. So we have the word mint. So mint has 4 different words, 4 different letters: M, I, N and T. So the total number of objects that we have is 4. There are 4 different objects, namely M, I, N and T. M, I, N and T. Now the question here is two letter permutations are. So the total number of objects are 4. And the question here is they are asking two letter permutations. So when they are asking two letter permutations, you have to select two items from these 4 and then you have to arrange them in a row. So first if I select M and I can arrange them like this, Mi and Im. If I select M and N, I can write it as Mn and Nm and so on. So these are the few two-digit linear permutations. Okay. Two-letter permutations are these things. Anyway, in this chapter we have to count how many permutations are there. We can count the number of permutations only if you can able to write down all the permutations, or we have to develop some techniques. If you don't know the techniques, what we have to do is we have to list down all the different two-digit permutations and then we have to count. Let's look into the second problem. The second problem is from the letters of the word running. So this problem is different from the first one. In the first one, the letters are M, I, N and T. All the 4 letters are different. But in the second problem, the letters are R, U, N, N, I, N, G. Here, all the letters are not different. There are 3 similar N's. In the previous problem, all the given letters are different. In this problem, all the letters are not different. Okay. So, from the letters of the word running, 3-letter permutations are. I have listed down 2-letter permutations and I have listed down 3-letter permutations. By 2-letter permutations, what you have to do is you have to select 2 and you have to arrange them. And if I ask for 3-letter permutations, you have to select 3 and you have to arrange them. If I ask for 4, you have to select 4 and you have to arrange them. So in the definition, we have similar or distinct. So the second problem is a case for similar and the first problem is a case for distinct. Now let us look into one more problem from the digits 1, 2, 3, 4 and 5. So the total number of objects that we have is 5 and the objects are 1, 2, 3 and 4 and 5. So the total number of objects that we have is 5. Now the first question is 2-digit letters or 2-digit numbers. 2-digit numbers means you have to select 2. So from the total 5 you have to select 2 and you have to arrange them. So 2-digit numbers are going to be 1 2, 2 1, 1 3, 3 1, 1 4, 4 1 and so on. So these are a few 2-digit permutations. So instead of saying 2-digit permutations, you can just say 2-digit numbers. And the second one is 3-digit numbers. So when I am asking for 3-digit numbers, what you have to do is you have to select 3 digits from these 5. I can select 1 2 3 or I can select 1 2 4. So 1 2 4, 1 4 2, 1 3 5, 3 1 5 and so on. So these are a few 3-digit permutations and these are a few 2-digit permutations. If I ask for 4-digit permutations, then you can select 4 and you can write down. Anyway, our prime motto in this chapter is to count how many permutations are there. Before going to count the number of permutations, you should be in a position to write down the permutations for simple cases. For the sake of completeness, we will look into the definition of circular permutation. The main difference between circular permutation and linear permutation is, in a linear permutation we arrange things in a row, but in a circular permutation we arrange things in a circle. And the definition is like this: from a finite set of similar or distinct things, selecting a few or all of them and arranging them in a circle is called as a circular permutation. So in order to understand this one, we can look into this example. So from the digits 1, 2, 3, 4, a few circular permutations are listed here. If I ask for linear permutations, then 1, 2, 3, 4, this is a linear permutation. Whereas this one is going to be a circular permutation. In a linear permutation, we arrange things in a row. In a circular permutation, we arrange things in a circle. Let us look into the differences between linear permutations and circular permutations. In a linear permutation, there is a notion of first element, second element, third element, and so on up to last element. But in a circular permutation, there is no notion of first element, second element, and last element. And the second difference is, few linear permutations result in a single circular permutation. You can see it using this example. So 1, 2, 3, 4, 2, 3, 4, 1, 3, 4, 1, 2, 4, 1, 2, 3. All these four linear permutations results in a single circular permutation. So this is the circular permutation. So here we have 1, 2, 3 and 4. If you read it from 1, it is going to be 1, 2, 3 and 4. If you read it from 2, it is going to be 2, 3, 4 and 1. If you read it from 3, 3, 4, 1, 2. If you read it from 4, 4, 1, 2, 3. So in general, we read circular permutations in clockwise directions. Okay. So if you consider this one, so there is no difference between these two circular permutations. These two circular permutations are one and the same. These two circular permutations are one and the same. But these four linear permutations are different. In a circular permutation, what you have to observe is, we cannot say the position. So if you take this linear permutation 1, 2, 3, 4, 1 is in the first position, 2 is in the second position, 3 is in the third position, 4 is in the fourth position. But when you come to this circular permutation, we cannot say that 1 is in the first position, we cannot say that 2 is in the second position, and so on. All that we can say is 2 is on the right hand side of 1, or in the clockwise direction of 1, and 3 is in the clockwise direction of 2, and 4 is in the clockwise direction of 3. So this is what these are the differences between linear permutations and circular permutations. Let us look at this example. So here they are asking us to list down all linear permutations and circular permutations using the digits 1, 2, 3 and 4 taken 3 at a time. The number of digits here are 4. They are 1, 2, 3 and 4. Now what we have to do is, we have to take 3 at a time and we have to write down all linear permutations, and later on we have to write down all circular permutations. So first let me take 1, 2 and 3. If you take 1, 2 and 3, these are the 6 different linear permutations that you can write using the digits 1, 2 and 3. And similarly, if you take 1, 2 and 4, these are the 6 different linear permutations that you can write using the digits 1, 2 and 4. And similarly, you can write down the remaining 6 and 6. These 6 linear permutations results in 1, 3 and 4. By taking 1, 3 and 4, you will get these 6 linear permutations. And the remaining is 2, 3, 4. If you take 2, 3, 4, these are the 6 linear permutations that you are going to get. Anyway, I encourage the students to pause the video and write down these 24 linear permutations on their own. So if you can able to write down these 24 linear permutations on your own, you will understand the pattern. Once you understand the pattern, you can count how many permutations are there. So we have listed down all linear permutations. These are the 24 linear permutations that we have using the digits 1, 2, 3, 4 taken 3 at a time. Now coming to the second part of the question, we have to write down all circular permutations. We have to take 3 at a time. The digits here are 1, 2, 3 and 4. First let me take 1, 2 and 3. So if you take 1, 2 and 3, we are going to get 2 different linear circular permutations. We are going to get 2 different circular permutations. That is, the first one is 1, 2 and 3. And the second one is 1, 3 and 2. These are the 2 circular permutations that you are going to get using the digits 1, 2 and 3. And these 2 are the circular permutations that you are going to get using the digits 1, 3 and 4. And these 2 are the circular permutations you can get using the digits 1, 4 and 3. And the remaining 2 result from 2, 3 and 4. So on the whole we have 8 circular permutations. And how many linear permutations you have? You have 24 linear permutations. And circular permutations, how many you have? You have 8 circular permutations. Definitely the number of circular permutations is going to be less than the number of linear permutations. Why? Because few linear permutations results in a single circular permutation. So here if you observe 1, 2, 3, 2, 3, 1, 3, 1, 2. All these 3 linear permutations results in the first circular permutation, that is 1, 2 and 3. So anyway, they didn't ask us to write down how many linear permutations and how many circular permutations. They just asked us to list down all the linear permutations and circular permutations. Our next motto in this chapter is to count the number of linear permutations. Without listing down all the linear permutations, we can actually count the number of permutations using this following theorem. And the statement of theorem is like this. If n comma r are positive integers and r less than or equal to n, then the number of linear permutations of n distinct objects taken r at a time is n times n minus 1 times n minus 2, so on up to n minus r plus 1. In short, we can write this expression using this notation: product k is equal to 0 to r minus 1 n minus k. When k is equal to 0, you are going to get the first term. When k is equal to 1, you are going to get the second term. When k is equal to 2, you are getting the third term. When k is equal to r minus 1, you are going to get the last one, that is n minus r plus 1. So when k is equal to r minus 1, n minus of r minus 1, which is going to be n minus r plus 1. So in the textbook they have given the proof of this theorem using mathematical induction. But here I am not going to use mathematical induction. I am going to use fundamental principle of counting. So let us look into the proof of this theorem. So in the previous example, So in this example, you have seen that the number of permutations of 4 distinct objects taken 3 at a time is going to be 24. And here we have listed down all the permutations. So number of permutations of 4 distinct objects taken 3 at a time is 24. So what we have done here is we have these 4 distinct objects 1, 2, 3 and 4, and we have to fill these 3 blanks using these 4 distinct objects, and the number of ways of filling these 3 blanks is going to be 24. So we have seen this one in the previous example. Now we will see how we will get this 24. So we have to fill these 3 blanks using these 4 objects. Now our task is to fill these 3 blanks. Now I am dividing this task into 3 parts, namely W1, W2 and W3. W1 is to fill the first blank, W2 is to fill the second blank, W3 is to fill the third blank. So let us see in how many ways we can do this work W1. So W1 stands for filling the first blank. We can fill this first blank using any one of these 4 objects. Therefore, the number of ways of filling this first blank is going to be 4. After filling the first blank in 4 ways, we will be left with 3 different objects. Now the next thing is we have to finish the work W2. The number of ways of finishing the work W2 is the number of ways of filling this second blank, and we can fill this second blank using these 3 different objects in 3 ways. After filling the first 2 blanks with 2 objects, we will be left with 2 more objects. The total number of objects is 4. We have filled the first 2 blanks with 2 objects. Therefore, the number of objects that are left is 2. Now, we can fill the third blank using these 2 objects in 2 ways. Now, the total number of ways of completing the task is equal to number of ways of doing the task is equal to number of ways of doing W1 times number of ways of doing W2 times number of ways of doing W3, which is equal to 4 times 3 times 2, which is equal to 24. We have seen this in the previous example. Now we want to generalize this one. So in the statement of the theorem, we have n different objects. I have n distinct objects, and we are interested in permutations with length r. That means I have to fill these r blanks 1, 2, 3, so on, r. Total number of blanks is r. Our task is to fill these r blanks. Now I am dividing this task into r different works, namely W1 is to fill the first blank, W2 is to fill the second blank, W3 is to fill the third one, and so on up to WR. WR is to fill the rth blank. Now the number of ways of doing W1. So W1 stands for filling up the first blank. Since we have n distinct objects, the number of ways of filling the first blank is going to be n. After filling the first blank with n different objects, after filling the first blank with one of the objects, the total number of objects that we are going to have is n minus 1. Now we have to complete that work W2. Number of ways of doing W2 is filling the second blank with one of the objects which are left. And the number of objects that are left is n minus 1. Therefore, the total number of ways of doing W2 is going to be n minus 1. After filling the first two blanks with two objects, number of objects that are left is going to be n minus 2. Therefore, number of ways of doing W3 is going to be n minus 2. So for the first blank, we have n objects. For the second blank, we have n minus 1 objects. For the third blank, we have n minus 2 objects. Therefore, for the rth blank, we will be having n minus of r minus 1 objects. Therefore, the number of ways of doing the work WR is going to be n minus of r minus 1, which is equal to n minus r plus 1. Now the total number of ways of completing the task. Number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2 times number of ways of doing W3 and so on, number of ways of doing WR, which is equal to n times n minus 1 times n minus 2, so on up to n minus r plus 1. So this is the proof. So basically we are using fundamental principle of counting again and again, or we are using the fundamental principle of counting in the extended way. So let us look into the statement of the theorem one more time. We are going to use this theorem left and right in this exercise and in the coming exercises also. Okay, so the total number of permutations of n distinct objects taken r at a time is going to be n times n minus 1 times n minus 2, so on up to n minus r plus 1. In short, we can write this using this notation: pi k is equal to 0 to r minus 1 n minus k. And then we have this following notation. The number of permutations of n distinct objects taken r at a time is generally denoted by npr or n of p comma r. But we'll use this notation npr. So whenever you see this notation, you have to read it as number of permutations of n distinct objects taken r at a time. If you read it as npr, you will not get the flavor of permutations and combinations. So you have to read it as number of permutations of n distinct objects taken r at a time. And now we have the formula for npr. Number of permutations of n distinct objects taken r at a time is n times n minus 1 times n minus 2, so on up to n minus r plus 1. So we denote this expression by npr. So our npr denotes this one: n times n minus 1 times n minus 2, so on up to n minus r plus 1. And by convention we denote np0 to be 1, or by convention we define np0 to be 1. Okay, np0 stands for number of permutations of n distinct objects taken 0 at a time. So we are not taking any objects, so we will not have any permutation. That is going to be the one permutation. So np0 equal to 1. And then we have this formula: npr is equal to n factorial upon n minus r factorial. So we can derive this formula here. But before deriving this formula, you should know what is the factorial. So I think you are familiar with factorials now. 10 times 9 factorial, you can write it as 10 factorial. Okay, and then 10 times 9 times 8, I can write it as is equal to 10 times 9 times 8 into 7 factorial upon 7 factorial. Now 8 into 7 factorial, I can write it as 8 factorial. Now 9 into 8 factorial, I can write it as 9 factorial, and 10 into 9 factorial, I can write it as 10 factorial. So on the whole, we have 10 factorial upon 7 factorial. Therefore 10 times 9 times 8, I can write it as 10 factorial upon 7 factorial. So similarly, our NPR is equal to n times n minus 1 times n minus 2, so on up to n minus r plus 1. Now what we are doing is we are multiplying and dividing by n minus r factorial. Now if you observe the numerator, it is starting from n, and all the successive digits are we are starting with n, and all the digits are 1 less than the previous one. N, n minus 1, n minus 2, n minus 3, and so on, n minus r plus 1, and the next one is n minus r factorial. Therefore the numerator is going to be n factorial, and the denominator is going to be n minus r factorial. Therefore the number of permutations of n distinct objects taken are at a time. That is our NPR. NPR is equal to n factorial upon n minus r factorial. So this is the formula that you have to remember. So I repeat, NPR is equal to n factorial upon n minus r factorial, but you should not read NPR as NPR. You have to read it as number of permutations of n distinct objects taken r at a time. Number of permutations of n distinct objects taken r at a time is equal to n factorial upon n minus r factorial. And then using that formula, you can derive what do you mean by NPN. NPN is equal to n factorial upon n minus n factorial, which is equal to n factorial upon 0 factorial, which is equal to n factorial, because 0 factorial is equal to 1. And now we have this interesting theorem. So the statement of the theorem is like this: if n comma r are if n comma r are positive integers and r is less than or equal to n, then NPR is equal to n times n minus 1 PR minus 1. So here the condition is r should be greater than or equal to 1. Okay. So I repeat, NPR is equal to n times n minus 1 PR minus 1. So this is the formula that you have to prove. So if you read it as NPR, then we have to actually prove it. So if you read it as number of permutations of n distinct objects taken r at a time, we can easily see the proof. Anyway, there are two ways of proving this theorem. The first one is using the formula, and the second one is using some combinatorial arguments. So first let me explain it using the formula. So what is your RHS? RHS is n times n minus 1 p r minus 1. So first let us expand this n minus 1 p r minus 1. So which is equal to n times n minus 1 factorial upon n minus 1 minus of r minus 1 factorial, which is equal to n times n minus 1 factorial upon n minus r factorial, and n times n minus 1 factorial is going to be n factorial. n factorial upon n minus r factorial, which is nothing but npr. Therefore, npr is equal to n times n minus 1 pr minus 1. So this is the proof using formula. But I am not interested in this formula. In this proof, I am going to give another proof using a combinatorial argument. Now, what does this NPR stands for? NPR stands for number of permutations of n distinct objects taken R at a time. That means we have n objects and we have to fill these R blanks, 1, 2, 3, so on up to R. We have these R blanks. So the number of ways of filling these R blanks using these n objects is going to be NPR. Okay. Now I am dividing this task into two parts. The first task is filling the first blank. And the second task here is filling the remaining R minus 1 blanks. So how many blanks we have remaining? R minus 1 blanks. Okay. Now, number of ways of doing W1. So W1 stands for number of ways of filling the first blank. Since we have n distinct objects, the number of ways of filling the first blank is going to be n. After filling the first blank with one of the objects, how many objects are going to be left with? We will be left with n minus 1 objects. Now we have n minus 1 objects and we have r minus 1 blanks. Therefore, the number of ways of filling these n minus 1 objects in these r minus 1 blanks is going to be n minus 1 p r minus 1. That is, number of ways of doing W2 is going to be n minus 1 p r minus 1. Therefore, the number of ways of completing this task is equal to number of ways of doing number of ways of completing this task is equal to number of ways of completing W1 into number of ways of completing W2, which is going to be n times n minus 1 p r minus 1. So with this we have completed